All right, ladies and gentlemen, 2 o'clock. Welcome back to your favorite class. Yes, thank you. Exactly. If I keep saying it, it'll be true. All right. That's at least the theory. Okay. Announcements. Homework 2 posted. That's posted a couple days ago. It's going to be due next Thursday. It'll be due the day before the exam. Your first exam is going to be in class next Friday, so a week from today. It won't actually be physically in class. You'll be taking it on Teams. I'll give a little bit more information on how we're going to do that next week. I will have an exam review session Thursday night, 7 p.m. We're going to go over practice problems, and I posted a set of practice problems for you guys to work through that I think will be at least somewhat representative of potential exam questions. So we've kind of covered, I would say, like 3 topics in this class up to the next Friday, and that would be like vector math, 2D particle equilibrium, and 3D particle equilibrium. So if you had to think about 3 potential questions that might be on the test, maybe that's what they're going to be. All right. And the questions that you see on the review session handout kind of follow that trend. So make sure to take a look at that. If you know how to do everything on that exam review, you will dominate. I'll tell you that. All right. The exam review is not turned in. The exam review is not graded. It is for your benefit. I have the answers posted for the exam review, just like I do for the homework, so you can work your way through it. I will also post the full solution for the exam review probably like early next week, maybe Monday or Tuesday. Okay. I just haven't had a chance to write it up yet. All right. Other questions? The question, will the exam review be recorded? Yes, the exam review will be recorded. Other questions? Okay. Then, as they say in Mulan, let's get down to business. But we're not going to defeat the Huns. We're going to do statics. Anyone see that? That movie's probably like before your time. Mulan came out in like late 90s, right? I think you guys are even like born then. When did Mulan come out? Like not the new one. Late 90s, you said? The first Mulan, the cartoon, the animated one. It was like late 90s. Man. Yeah, that's true. You guys still probably watch it. Like, Snow White came out before I was born. I still watched that. So I guess I shouldn't be so quick to judge. All right. So last time we were looking at how to represent 3-dimensional vectors using sort of our rectangular unit vector composition. So writing 3-dimensional vectors in terms of like I, J, and K. And we saw some cool relationships that exist between if we write a force in 3-dimensional components, and if we happen to know the cosine of the angle between the force and the various axes of interest. So we'll just review last time. We were sort of talking about direction cosines for 3D vectors. Oh. Okay. And we had a general picture maybe that will help us on our way. And it looks like this, where we have our traditional XYZ coordinate system. And we said that if we had some force that existed out in space here, just some arbitrary force, F, that if you happen to know the angle between that force and the various axes, and we label those particular angles as like theta x, here's theta y, and best I can here, theta z. So if you know the magnitude of this force, and you know these particular angles, then you can represent the force in terms of its components, which is like the force in x, the force in y, and the force in z, with the following, and that is the magnitude of the force times cosine theta x I hat plus magnitude of the force cosine theta y and j hat and magnitude of the force cosine theta z and k hat. Kind of a combination of the 3. We're saying that each one of these is like the vector component along those general principal directions. So here this was like our fx. Here's our fy. And this is like our fz here. So it's those vectors along those particular directions. We can resolve them as such. We also showed that there's kind of like a shorthand for these directional cosines. So in shorthand, we had that like L is cosine theta x, M is cosine theta y, and then script N is cosine theta z. Okay. So we could alternatively represent the equation above for our force using that script L, script M, script N. And we also saw that, for instance, L squared plus M squared plus N squared is equal to 1. Okay. Kind of an interesting little trick there. Okay. Now, it's nice to represent that force in these rectangular components. And we sort of did an example of this at the end of last lecture, where we had a force out in space and the angles between the axes of interest and the force that we created so that we could resolve it into its directions. And then maybe after that, we can do like some of the forces equal 0 and things like that. Okay, it's a very nice concept. However, we may be interested in representing this force in an alternative method that will also help us with some analysis. And we also may be interested in, let's say we have a force along a particular direction. And we've talked about sort of the importance of unit vectors so far in this class, like defining a vector of value 1 in the I direction, a vector of value 1 in the J direction, and the K direction, X, Y, Z, and how these are helpful for analysis. We'll also, going forward, want to be able to define unit vectors not just in I, J, and K, or X, Y, and Z. We also might want to define some unit vectors in some other critical directions. And specifically, if you have a force in an arbitrary direction, you might want to define a unit vector in that direction to help you with analysis. And I'll show you why that is in just a second. But for now, let's just talk about how we might want to create a unit vector in the direction of a force. And we'll see how this is useful and why this is useful in just a second with an example. All right. Let's remember, my computer's like kind of laggy today. Let's see what happens if I go to a new sheet here. Maybe it'll be less laggy. I think this is going to be a little bit less laggy. So let's recall that we can write a force as like the magnitude of that force in the x direction I hat plus the magnitude of that force in the y direction. I'll just represent it as Fy with no bar over the top. That's representing a magnitude plus force in z k hat. These are specifically magnitudes. Or if we let the magnitude of the force, let's just drop like the bar notation and just call it capital F without the bar on top of it. So not a vector, but this is a scalar value. We know that this is going to be something like the magnitude of F multiplied by cosine theta x I hat plus cosine theta y j hat plus cosine theta z k hat. Okay, so resolving that force into its directions along I, j, and k. All right, using the directional cosines that we just talked about. Right. So if I were interested in creating a unit vector along the direction of this force, well, the way that I can do that is just, I have a force in a certain direction. If I just normalize that force by its magnitude, that would be a unit vector in the direction of that force. What do I mean by that? So if I divide F by the magnitude of F, would be a vector in the direction of the force of magnitude 1. Right? So whatever the force is, let's say 800 newtons directed in the direction of that force, whatever that is, and I normalize that by the magnitude of that force, 800 newtons, then the resulting vector is just going to be a vector of magnitude 1 in the direction of the force. And that's what I'm kind of like getting at with this equation here. So if I divide both sides by this magnitude of this force, so then I have this force F. I'm going to divide it by the magnitude of this force here. So it's this vector F divided by its own magnitude. Using my directional cosines, this is just going to be cosine theta x I hat plus cosine theta y j hat plus cosine theta z k hat. I'm going to relabel this here as unit vector lambda. All right. So this is the vector F divided by its own magnitude. Right. And because of what we know about the directional cosines, it's just equal to this sum of the individual cosine components along those various directions. So in short, a unit vector along a force may be defined as, here, this lambda, which is the force divided by its own magnitude, which we know is the sum of the directional cosines in the various directions. Okay, and this is an important result, and we will use this. And let's give some pictographic representation of what's actually happening here. All right. Give you a second to finish copying down if you need to. So what do we mean here? What is this sort of math actually representing physically? Here we have x, y, and z. And let's say I have some force. F. Well, if I wanted to like be clear about defining a unit vector in that direction, then I would say that that force F could be written as the magnitude of the force directed along a unit vector lambda that's in the direction of that force. All right. So the unit vector, remember, is of magnitude 1 in the direction of the force. Multiply 1 by the magnitude of that force, and you will have the force vector, F. Okay? So the idea here is that we have this force in this particular direction, and also in that same direction is this unit vector lambda down here, right? So of magnitude 1. We know that this force can be broken down into components in like Fx, Fy, and Fz. So that would be like here, Fx, which we know is cosine theta x I hat multiplied by the magnitude of the force. Maybe there's some component here coming out at us that's like Fz. And I know this is going to be a little strange. Maybe I'll rewrite this as here. This is the magnitude of that force. Cosine theta z in k hat. And I have some component up here that is Fy, which is the magnitude of this force, times cosine theta y in the j hat. Sorry for kind of crossing over lines there. All right. This unit vector lambda can also sort of be broken up into its individual directions, right? And this would have like individual directional components here, here, and here, which like run in the I, J, and the K directions. Where this here would just be like cos I hat. It is the component that tells us which direction that we're in for this particular force, all right? So the force X, you know, has some magnitude of F times cosine theta X, and it's directed in I hat. Okay. And you could repeat for the other directions. So in short, what we're getting here is we're getting that our force, which is the magnitude of the force in I hat plus the magnitude of the force y in j hat plus magnitude of the force z k hat can just be broken up into what would be unit vectors in these various directions, which might be something like, well, let's just do it this way. Magnitude f cosine theta x I hat plus magnitude of f cosine theta y j hat plus magnitude of f cosine theta z k hat. So it's just another nice way to represent my force. And if we have my unit vector lambda here, which I know is cosine theta x I hat plus cosine theta y j hat plus cosine theta j z k hat. Then components of the force in x, y, z directions are just something like this. And we can make little shorthands for these guys, where we say that this is like the part of the unit vector that's in the x direction. This is the part of the unit vector that's in the y direction. And this is the part of the unit vector that's in the z direction. And so you might see the component in the x direction written as the magnitude of the force just times this component of the unit vector along that force in the x direction. All right. So we're just kind of giving you these tools and building these tools that will help you define forces along various directions. All right. Now it's just kind of arming your tool bag and getting you ready to actually do analysis. So with these tools in hand, let's see how they're actually used. All right. So let's try sort of a practice problem here. Okay. We have a force here with components x 20 pounds, y negative 30 pounds, z 60 pounds. We want to determine the magnitude and the angles that it forms with the coordinate axes. I'll give you a second to copy that down. Okay, let's give this a go. I'll put the important information here. See if I can just copy paste this. Look at that, baby. It's got components, 20 pounds in x, negative 30 pounds in y, 60 pounds in z. I want to determine its total magnitude and the angles that it forms with the coordinate axes. All right, so let's see if we can sort of sketch this guy first. So here's x, y, z. I'm going to give myself a little extension of the y-axis into the negative direction. All right, so in x we have 20 pounds, y negative 30, and z 60. All right. So this is just like defining a location for this force in space. It's like 20 in x, negative 30 in y, and 60 in z. All right, so if I'm 20 in x, maybe I'm here on the x-axis. If I'm negative 30 in y, maybe I'm here on the y-axis. If I'm in 60 in z, I'm going to be like way out here. All right, so I've got a vector that's kind of like pointing down. It's kind of hard to draw this, but sort of like pointing down and kind of coming out at me. It's a little bit hard to sort of render this in 3D, but sort of got that sort of look to it. So here's my vector f. All right. First, I want its magnitude, F. And remember that the magnitude of the force is the square root of the sum of the squares of the components. So it's the magnitude of the force in the x direction squared, plus the magnitude of the force in the y direction squared, plus the magnitude of the force in the z direction squared. Right. So it'll be 20. I'll just work in pounds. I'm not going to put the units in here, but we know that this is in pounds. 20 pounds squared, negative 30 squared, plus my force in z, 60 squared. Units here are going to be pounds. Work this out. I'll have a magnitude here. It's going to be the square root of 4,900. Very convenient. Square root of 4,900 pounds squared. Or if I take the square root of this, 70 pounds. Okay. So that's the magnitude of my force. And maybe I kind of put that in here. Remember, this is the magnitude of the force here in the direction of the force, this unit vector lambda. So my force is 70 pounds directed along lambda, where lambda is the unit vector along this force. Haven't really defined that yet, but we can in just a second. Okay. So the next bit of this problem here, I want to find the angles that this particular force forms with the coordinate axes. All right, so what are these angles? Theta x, theta y, theta z. All right. Well, remember, those are like the angles here between this force and the x-axis. You've got this angle here, which is like the angle that forms between the force and the y-axis, and also this angle here that forms between the force and the z-axis. Okay, that's what we're after. Okay, a couple of different ways that we could do this. I think probably the easiest way is to know that our force is typically written as the magnitude of the force cosine theta x I hat plus magnitude of the force cosine theta y j hat plus magnitude of the force cosine theta z k hat. And that this here is the component of the force that's in x. This is the component of the force that's in y. And this is the component of the force that's in z. You also know that like the magnitude of the force in the x direction is given in the problem originally, just 20 pounds. The magnitude of the force in the y direction is given in the problem, negative 30 pounds. And the magnitude of the force in the z direction, given in the problem, 60 pounds. All right. Also know, trying to think of the easiest way to get to this. The force in x is the magnitude of the force times cosine theta x I hat. So we know the force in x is the magnitude of the force in x I hat, which is the total magnitude of the force cosine theta x and I hat, or in short, that the magnitude of force in x is magnitude of force cosine theta x. So this magnitude of the force in the x direction, given in the problem, 20 pounds. This is equal to the total magnitude of the force, which we found before is 70 pounds, times cosine theta x. And you can work this out and find that your angle theta x here will be 73.4 degrees. You can go through a similar process for the y and the z directions. Magnitude of the force in the y direction in j hat is the total magnitude of the force multiplied by your unit vector cosine theta y in j hat. So here, this guy equaling this guy. I have these things again. So magnitude of the force in the y is negative 30 pounds. The total magnitude of the force is 70 pounds times cosine theta y. I solve here. The angle that I'm making with the horizontal, 115.4 degrees. Lastly, the magnitude of the force in z in k hat is equal to the total magnitude of the force times cosine theta z in k hat. All right. Magnitude of the force in z, this was given as 60 pounds. Equal to the magnitude of the force total is 70 pounds times cosine theta z. And you're going to end up with a theta z here after sort of working through the inverse cosine, which is 31 degrees. All right. So just kind of like manipulating some of our direction cosines, understanding like what the full force is, normalizing each particular force and its various directions to come up with our various angles. Okay, so that's that. All right, I think we can continue and keep working. Last topic we'll do today is creating a unit vector between 2 points in space. Often it's helpful to define a unit vector along a particular direction between 2 points in space. And one example might be is if you have like a rope that exists somewhere in the room tying one point of that room to another point, okay? if I know the distance between that guy and that guy, it might be helpful to define a unit vector along that particular location so that I can define like the force in that general direction. All right. So often we need unit vectors between 2 points in space. So let's make a figure of this and draw what this looks like, and we'll talk about how to make this. Okay, so I have a point in space here. Let's call this, I don't know, P1. And it's got coordinates which are x1, y1, and z1. All right. And then there's another point in space up here. I'll call this P2. And this has coordinates x2, y2, z2. And so let's say that we have a vector between those 2 points. Let's say it's some force vector that exists between those 2 particular points. And thus there's a unit vector that we could find that exists between those 2 points here. Trying to like overlay this, my thing is kind of freaking out. All right. And let's call this just like lambda. I'll just call it lambda for now. All right, it's this unit vector that exists between these 2 different points. So vector from P1 to P2 is F directed along lambda. All right. Now, if I thought about like the distances between these 2 points in these various directions, I can write that directly. I'll say distance between points in each direction given by, let's say the distance in x is just going to be the coordinate x2 minus the coordinate x1, obviously. The distance in y is y2 minus y1. And the distance in z is z2 minus z1. Right. So you're kind of like making what is like this box. It's kind of hard to draw on this figure. There's a better picture in your notes here. Okay. If you've got this force directed from this particular point to this particular point, it's calling it M and N in your notes. But the distance along x is x2 minus x1. The distance along y is y2 minus y1. And the distance along z is z2 minus z1. Okay. Then here the vector between P2 and P1 let's call it vector mn, since it's kind of m and n in this picture, is just the distance x in I plus the distance y in j plus the distance z in k. It's the combination of the contributions in those like principal directions, right? Distance between P1 and P2. We'll just use our sort of vector formulations here. And let's just call this D, little d. It's the square root of the sum of the squares. You may have learned like this distance formula in your math class. All right. So if we wanted a unit vector directed along that particular direction, we would just take that vector, mn, that distance vector, and then normalize it by its total distance to get a unit vector in that direction. This vector mn, or directed between points P1 and P2, divided by the total magnitude of this vector mn, is going to give me this unit vector in that general direction, lambda. All right. So this guy has a magnitude in a direction. Its magnitude is whatever that distance is. And the direction obviously is the direction that that guy's pointing. Right? If we normalize this by the total magnitude of that guy, then the vector that we're left with has a magnitude of 1, and it's going to be pointed in the direction of this original guy. All right. So in that case, my vector, which is the vector mn, we know this as the distance in x and I hat plus the distance in y, j hat, plus distance in z, k hat, normalized by the total distance, which is the square root of the sum of the squares. That's like dx squared plus dy squared plus dz squared. All right. So if the force is along the line, then the force is whatever the magnitude of the force is multiplied by that unit vector. All right. This happens often. This is used often. Okay. And I'm just going to talk through this example for now, and then we'll actually tackle this example on Tuesday. Actually, let me get it in as a picture. Okay. So here's an example. We've got this wire that's connected between point A and point B in space. All right. I know the distance between point A and point B. Okay. Those distances are like, if we label this as X, Y, and Z, then the distance from A to B in the X direction is 30 meters. Sorry, 40 meters. The distance from A to B in the Y dimension is this 30 meters. The distance from A to B in the Z dimension is 80 meters. Okay. So like the distance I travel in X is 40. The distance I travel in Y is 30 meters. And the distance I travel in Z is 80 meters. Okay. So the force that exists in this wire between A and B is whatever the magnitude of that force is, multiplied by the unit vector that exists between points A and points B. Right? And so if I want to calculate, or I want to determine what this unit vector is, I need to use like the dimensions of the problem to determine, okay, well, what is the unit vector here pointing from A to B that I'm going to use to define where my force is acting. Okay. So I'm told that the tension in this particular wire is 2,500 newtons. All right. So I need to know what is this direction that it's pointing so that I can properly segment it into its like X, Y, and Z components. That's what it's asking me for in this particular problem. All right. And I'm going to do that by understanding that this lambda AB can be made by taking dxi hat plus the distance in y j hat plus distance in z k hat normalized by the total distance between those 2 points. Okay, so that's the idea. That's the flavor. It's the motivation. So we'll call it here, and we'll actually go through this example fully on Tuesday. So that's it for today. I hope you guys have a nice weekend. Even though it's rainy out.